All right. Well, hello, Discrete Math. Thank you for joining me today. Yesterday, we got a chance to talk about what were called the Fibonacci numbers. We got to see how the numbers came about, as well as kind of where they were used in the real world, or where they come up in the real world. Today we're going to continue by looking at some more kind of interesting patterns and numbers. We're going to focus today on what's called the golden ratio. Today's going to focus more on the numerical side of the numbers behind the golden ratio, and then in the next couple of sections we'll be applying the golden ratio into some real world context. So to start off with, the golden ratio is one of the most famous, most studied math numbers in all mathematics. In fact, I can tell you firsthand that I'm currently working on my master's in mathematics, and even to this day, we're still talking about golden ratio. The Greeks thought that it was so important they gave it mystical powers or mystical properties, called it a divine proportion. It's taken on a whole bunch of different names since then, such as the golden number, the golden section, and today in modern times we consider it to be what's called the golden ratio. The way that we typically denote the golden ratio is with the Greek lowercase letter phi. So it looks kind of like a circle or an O with a slash through it. That's going to be the notation we'll use to denote the golden ratio. So the golden ratio, it's an irrational number, so think of it in terms of pi, or think of it in terms of Euler's number e, so it goes on forever, cannot be written as a fraction. Most times you can just use the decimal approximation. If you're wondering what that was, I've got that there for you. It's approximately 1.618. If you wanted to know the exact value, here is that golden ratio. So phi is equal to exactly 1 plus the square root of 5 over 2. And again, if you were to type that into your calculator, you would find out that to 3 decimal places, which is usually good enough, it's approximately 1.618. You might kind of notice that that looks very familiar. It looks very similar to something we were looking at in the lesson from the Fibonacci numbers. In fact, those are going to actually come back up within this section as well. So part of the golden property was that there was this search to find a positive number that when you add 1 to it, you get the square of that number. So to solve that, really what it breaks down to is it's just a quadratic equation. And that quadratic equation that I've got written for you there is x squared plus x minus 1. So that's this equation right here. In order to solve that equation, you would just rewrite it as x squared minus x minus 1 equals 0, so solve for one side to be 0. And then I went ahead and showed it here using the quadratic formula, where you would have that a is 1, that b is negative 1, and that c is negative 1. And when you plug all that in, and again, I'm not going to make you go through all that work, you end up with an answer of 1 plus and minus the square root of 5 over 2, which you notice is very similar to what we said just on the slide before, which was that the golden ratio is 1 plus the square root of 5 over 2. And so notice that the only difference is that there's a plus and minus sign. So that's what we're going to talk about on this next slide. So of those two solutions, one of them is negative, which is that if you take 1 minus the square root of 5 over 2, you get negative 0.618. The other one is what's truly the golden ratio, which is just that 1 plus the square root of 5 over 2. And I think there was a typo in there. So keep in mind that this first one would be taking 1 just minus the square root of 5 over 2. That's how it's coming up with this negative value. The second one, we are restricting it to just be the 1 plus the square root of 5 over 2, which gives us that positive version. So we call this property golden property, and as we're going to see, it's going to have some really important algebraic implications today, and then geometric implications later on in this chapter. So Fibonacci numbers and the golden property, let's kind of talk about how this works. So when we use the golden property, which we know phi squared is equal to phi plus 1, we can use that to recursively compute higher and higher powers of phi, in much the same way that we would with Fibonacci numbers. So starting with the original equation of phi squared plus phi plus 1 equals phi plus 1, we're just going to multiply each side of that equation by phi. So we're going to multiply this left side by phi. We're also going to multiply this right side by phi. And keep in mind that when we multiply the right side by phi, we're putting that in parentheses, meaning that we're going to distribute phi to each of those terms. Once we do that, we end up with this equation right here. When you then replace phi squared by phi plus 1, which is what it's equal to, you get this equation. So you get phi to the third power is equal to phi plus 1 plus phi, and then when you combine your like terms, you find out that phi to the third power is 2 phi plus 1. Okay, so if we continue that process, so now starting with the equation we just finished with, phi to the third power is equal to 2 phi plus 1. If we multiply each side of that equation by phi, so multiply left side by phi, multiply right side by phi, and again on that right side, make sure that you are distributing. So put the 2 to the phi plus 1 in parentheses, distribute phi to each of those terms. You're going to end up with phi to the fourth power is equal to 2 phi squared plus phi. Now again, we're going to take phi squared and replace that with phi plus 1, which was our very first equation. So when you do that, you end up with this equation. Again, you distribute the 2 to each of those terms, and then you end up combining like terms to get 3 phi plus 2. And if you continue to do that, I'll kind of spare you the details of all of that. But when you get to phi to the fifth power, you get 5 phi plus 3. And if we continue to do this, here's what you're going to end up noticing. Phi to the sixth power is 8 phi plus 5. Phi to the seventh power is 13 phi plus 8. Phi to the eighth power is 21 phi plus 13. Which if you look, and it's probably easier to see from the right side of the equations first, is that you're actually going up by the Fibonacci sequence. And the same actually is true on the left side. It's just one term further on in the Fibonacci numbers. So the general formula that we can use to express higher powers is in terms of the Fibonacci numbers, and it's written as follows. So here is your powers for your golden ratio. So if you want to find phi to the nth power, you take the Fibonacci number n, so the nth Fibonacci number multiplied by phi, plus the n minus 1th Fibonacci number. So you can see how what we talked about in the first lesson is now getting brought into what we talk about today. So we're now going to explore what's probably the most surprising connection between the Fibonacci numbers and the golden ratio. We're going to take a look at what happens when you take the ratio, and what we mean by the ratio is we're going to divide by consecutive Fibonacci numbers, and we're going to kind of see how that works. The table that's on the following slide is going to show the first 16 values of the ratio of f sub n divided by f sub n minus 1. So when you start by taking the first two Fibonacci numbers and dividing, 1 divided by 1, you get 1. When you take the second 2 and divide, well, really the second and third terms, you get 2 divided by 1 is 2. When you do it a third time, 3 divided by 2 is 1.5. And then as you continue, you can notice that they're starting to get closer and closer to some number. We're now at 1.666, just 1.6, 1.625. Now we're at 1.61, 1.61. Let's see what they get closer and closer to. So on the next slide, 1.617, 1.618, 1.61. If you round it, would be 1.618. 1.618, 1.618. Now we're actually consistent all the way out to 5 decimal places. 1.61803, 1.61803. Which is kind of interesting because, let me go back real quick, this 1.618 is exactly what we found as the number for phi. So it shows an interesting pattern. As n gets larger and larger, the ratio of consecutive Fibonacci numbers, again, it looks like it's getting to a fixed value. And that fixed value turns out to be the golden ratio. So just another formula is that phi of n divided by phi of n minus 1 is equal to phi. So that's kind of another equation that you can use to help find phi if you're wanting to approximate. And then just a side note on that, the larger your value of n gets, the better the approximation is. So yeah, I think that was all I had for you guys today. I'm trying to keep these videos short and sweet for you. Don't forget, if you want to be working on homework, to be working on that. Also, don't forget that there is going to be a quiz this Friday. That's just an optional quiz to make sure, or for you to check to see how you're doing. And yeah, we're kind of building up towards that next midterm, which will be at the end of this month. Remember that second midterm can be used to replace your first midterm if you didn't do so well on the first one. And then We'll also have an optional final. Again, that would be another chance for you to try to get your grade up by increasing your first midterm grade. So if you're wanting to try to do that, if you're wanting to try to get your grade up, continue watching these videos, continuing practicing with those quizzes, continue getting ready for those midterms, and I will see you again next time. Have a good rest of your day.